Alright, so for this problem what we have is a block of wood floating in some liquid. We won't call it water because we don't want the W of the wood to get mixed up with W of water. Let's just call it liquid. So we have basically it's just bobbing up and down like this, and yeah, that's about it. So we're just going to describe the motion here. So first of all, what is the condition for the block to keep afloat? Well, that one's pretty easy. It's just for the density of the wood to be less than the density of the, I guess less than it or equal, I suppose, than the density of the liquid that it's floating in. So the moment it becomes more dense, then it will just sink to the bottom. Alright, easy. We're going to look for the equilibrium height of the block above the water. So the top of the block to the water, that distance is z. So what is the equilibrium height? Let's go ahead and write out real quick the equation of motion, just because we'll need it later on anyway. So just mass times acceleration in the z direction, just equal to the sum of forces. So what do we have? Well, let's start with the easy one. What do we have going downward? We have the mass of the block multiplied by the acceleration due to gravity. Alright, m is I'm just calling that the mass of the block real quick. We'll fill it in with these densities in a moment. And then pushing up, we just have the buoyant force, which is it's just m, the mass of the water which has been displaced here. So well, yeah, for now okay, I said water, let's just call it liquid again. We don't want to get W's mixed up. The mass of the liquid displaced multiplied by g. Alright, so I'll fill in the masses real quick. I'm just going to call the cross-sectional area of this wood block or dowel or whatever this is, cylinder. I'll just call that A. So the mass of the block is A times the height of the block times the density of the block, rho W. Okay. And then here's the mass of the block again. A, height, rho wood, G. Okay, so now now for the mass of the displaced liquid, we have A. Instead of height, we have H minus the part that's above the water, so H minus Z. And then the density of the liquid, and then gravity. Okay, so this will just divide out nicely. At least the A will. Let's just divide everything by this term out front, so we just end up with this acceleration here. So that will all divide out, so we just get a minus g. Okay, and then we have a plus. The A is going to divide out. We have an H plus Z divided by this H. We have the rho of the liquid minus or divided by the rho of the wood, mass density, and then we have G. Okay, so what we could have just done is set these two forces equal to each other, but that's what we'll do now. So here is sort of the equation of motion here in the z direction, which is the only direction we're worried about. For the equilibrium height, so we're going to find z eq. We'll set the acceleration in the z direction to 0. Just call this, oops, ZEQ. All right, so that just gives us this term inside, or this group inside here is equal to 0, which just means that G is equal to G multiplied by H plus Z over H. The density of the liquid divided by the density of the wood. All right, we can divide both sides by G. And again, what we're trying to get here is this Z. So let me write the little EQ right here so we remember this is only the equilibrium position that we're going for here. All right, so what do we got? We have ZEQ. I keep writing a G, I mean Q. Okay, so these G's are going to divide out. This row W for the wood will get flipped up on the top, and this row L for liquid will get flipped onto the bottom. We will multiply by H, and then, okay, so all we have to do now is subtract the H off. So here is our equilibrium position. All right. So, so now what we want to do is calculate the motion of the block. So, one thing I'm going to do is just move into a frame of reference where we're with reference to this equilibrium position. So I'm going to use let's call our z coordinate equal to the equilibrium position plus the displacement from the equilibrium position, which I'll just call that this cursive z. All right, so let's go ahead and plug that into our equation of motion right here. So taking two derivatives with respect to time, this ZEQ here is just it's a constant, so that will go away. So we end up with cursive Z double dot equals minus G plus, let's write this row. So again, we're looking at this equation right here. Rho L, rho W, we have a G over H, and all I have left to put in is this H plus Z, which I'm going to plug in this H plus ZEQ plus this squiggly one. All right. Let me make sure this looks good. I think I made a mistake here. Where did I make this mistake? Somehow I lost this minus sign here. This is a minus sign. I don't know how I did this. So what is that going to do? That's just going to change this minus sign here to a plus. All right, I don't know how I did that, but I did. Okay. Oh, gee. All right. Which in turn, we have a minus sign here and here. All right. Okay, so H minus the cursive Z. All right, now let's plug in this constant ZEQ. So we're just subtracting it. It's a rho W over rho L multiplied by H, and then a minus an H from right here. Okay, so see what we get. We have a minus G. I'm just going to take this outside part and multiply it term by term into this thing. One thing though is this H and this H are going to get rid of each other. We'll have a minus sign in each. So we have a rho L over rho W G over H. Okay, and then multiply just by this curly Z. And then minus this rho L, rho W, G over H, multiplied by rho W over rho L. You can see where this is going, right? H. Okay. All right, so these will divide out, these will divide out, these will divide out, and we're left with just a minus G, which ought to be a plus G, right? So I must have missed another minus sign here somewhere. Not a good day for minus signs, I think. All right, after some searching, I found where my mistake was. So after I fixed this first minus sign problem here, so I changed this minus sign here, then I didn't change this equation correctly. So there should be another minus sign right here. All right, because what I was doing, basically, I was solving for minus ZEQ. And so I fixed this part, but I didn't fix this part. Okay, so with that change, now this is a plus sign right here and right here. And I think that's it. I think. All right. So now we have this minus G and plus G that go away. So this is a huge mess. So what we've got now is this, let me put a tail on this so we know it's not a 3 or something. We have this second derivative with respect to time of this cursive z, which is it's just the, again, the displacement from the equilibrium point, equal to just this term right here. So minus rho L G over rho W H Z. Cursive z. Okay. So finally, we get this simple harmonic oscillator equation, which is exactly what we would expect, right? It's just going to, you displace it slightly, it will just bob up and down. Without a damping term, it'll just do that forever. And so, by the way, the frequency of this oscillation is going to be rho L G over rho W H under the square root. Okay, so we've solved for the motion if we don't have any friction, right? It's just a sinusoidal motion. So now suppose there is friction, a viscous friction between this block of wood and the liquid around it. So what that does is it introduces another term in our badly patched up equation of motion here, which, let's see if I can find this. So here's some forces, but what we've already done with this one is we've already divided by the mass. So let me just write this out real quick. So if we have this force of friction, and it's a minus B, and then the velocity of this block, right? Let me just write it as a magnitude here. V is just z dot, right? All right, so it's always opposing the motion. So this force can be put directly into this equation, but but we are going to well, actually the equation I want to use is this one right here. One real quick, obviously if we look at our substitution that we made, because this is a constant, the z dot is just equal to this cursive z dot, right? Because this one's constant, so that will go to 0. So I'm just going to go ahead and use this equation, and so rather than B, I'm going to use a capital B. So this is the force, I guess, divided by the mass of the block. All right, and I'm going to put a 2 there. So, and the reason for this will be clear. All right, and I'm going to use the curly z, or the cursive z. So all I've done is rewritten this force. It's the same force, right? This z dot here is going to be equal to this cursive z dot, and I'm using a different constant because of how we divided by the mass up here, and I'm also putting a 2 in there. So this constant is, aside from this, well, once we divide by the mass, the constant's going to be 2 times as small. So anyway, whether or not we end up piecing it back together with this original small b, we may not do that. We'll just solve it in terms of this big B. All right, rewriting our equation of motion, again using this one instead. So we have minus rho LG over rho WH Z, curly Z, and then this force will also be added on. All right, so let's rewrite this in terms of, I'm just going to bring everything over to 0 and just kind of set it up in a nice form. So plus 2b, so I'm just putting the derivatives, that's a really derivatives in order, so double dots, dots, and then just the z itself. Okay, all right, so we can use a trial solution. It's some constant multiplied by an exponential with some lambda, and it's a function of t, okay? And so putting that into here, what do we end up with? Well, we end up with lambda squared. So 2 lambdas are coming down for this guy, and then we have this whole function again, which we'll just call z, plus 2b. This time only 1 lambda comes down, plus this rho L G rho omega H. All right, so now the z's go away, and we just have a characteristic equation, so for lambda. All right, so now we'll see why we chose this 2b instead of just a b. So just using the quadratic formula, first you take a negative b minus 2b plus or minus the square root of b squared, so 4b squared minus 4 times ac So there's 1, so 4, and then the C term here. Alright, maybe I should have called that something so we don't have to deal with all this. All divided by 2a. So in this equation, a is the coefficient of this lambda squared, which is just a 2. Alright, so this is going to simplify, and the 2's are going to divide out, so that's why we picked this 2b instead of b. To be or not to be. So so these 4's I'm going to factor out as a 2 and cancel with those others. And so now we just have a b squared minus this awkward rho g rho w h thing under a square root. All right, so so basically now what we could do is plug this lambda back in here. So some amplitude e to the minus b t, and then e to the plus or minus this b squared minus rho g h multiplied by t. All right, so how is the equation of motion changed? Well, for one thing, now we have this real exponent up here. B is greater than 0, and so there's this damping term. So whether or not it oscillates, it's going to damp to 0 in the end, right? So that wasn't there before. Whether or not, so it can also be overdamped, which would mean that this entire term here is also real. All right, so for overdamping, b squared is greater than this rho L G over rho omega H. In which case this is also real, and obviously the physical solution is to take this this negative sign here for damping. Well, or even I guess even if we take the plus sign, right, the inside will still have something less than b, so this one will still win. Okay, all right, so yeah, maybe we can take the plus sign. But if b is less than, or if b squared is less than this rho Lg rho omega H, then it's underdamped. And that's when we get, this is imaginary under here, and so we still get oscillation. So though it's not at the same frequency as before. So anyway, so overdamping, if you were to plot this displacement z as a function of time, overdamping, it would just head straight to 0 with no oscillation whatsoever. With underdamping, I'm not going to be super careful with this, I guess, but you get sort of this oscillation that will damp away to 0. So that's how this the motion of this block is going to be changed as a result of adding some viscosity to the fluid. And yeah, it would also be good to, I guess, solve for the various frequencies and things like that. But you can just kind of see how that would be, how that could be done. We'd factor out a minus sign from this, so we would we'd get an e to the I, and then we'd have this rho Lg over rho omega h minus b squared. And here's our frequency. Right there. All right, so since this b squared is positive, we're subtracting something positive from, this was our original frequency from before, wasn't it? Right, this rho Lg over rho Wh. So our frequency is smaller than it was